In this study, we explore how to enhance image generation using variational autoencoders, VAEs, and generative adversarial networks, GANs, through unsupervised learning. By leveraging a method called feature perceptual loss, which utilizes a pre-trained deep learning model to assess image similarity, we shift from traditional pixel-by-pixel comparisons. Our experiments on a dataset of face images reveal that our approach yields significantly better image quality compared to existing models. Additionally, the latent representations created by our VAE effectively capture complex information, demonstrating remarkable prowess in recognizing and predicting facial attributes, thus achieving top performance in this area. Method. This section begins with a detailed enumeration of various facial attributes related to appearance, including features like mouth, narrow eyes, and traits such as oval face and pale skin. Each characteristic is essential for facial analysis, possibly to create a profile for facial recognition or modification. These attributes suggest a focus on recognizing and manipulating facial features through a computational lens. Next, the paper transitions to discuss the performance metrics of several models responsible for predicting these facial attributes. Notably, it measures their accuracy, as seen in the comparative Table 1. This data showcases the effectiveness of different algorithms, including FaceTracer, Panda with its two variants, LNets plus ANet, VAEZ, and VGGFC. The reference to truth landmarks indicates that some models utilize precise facial landmark points to enhance their predictions about facial parts, contributing crucially to their accuracy. A fascinating technique described involves manipulating latent vectors. These are crucially the abstract representations of facial images. The authors explain that specialized vectors for attributes can be combined with these latent vectors through basic vector arithmetic. For example, adding a vector representing a smile, denoted with a parameter, to the latent representation of a non-smiling individual results in a smooth transition to a smiling expression. This ability to seamlessly alter facial expressions while maintaining other attributes hints at a sophisticated understanding of how various facial features interrelate. The next subsection, titled Correlation between Attribute-Specific Vectors, dives into the relationships among different facial attributes. The research utilizes data from the Celebé dataset to calculate vectors for 13 specifically chosen attributes. The correlations between these attributes are then visually represented, showcasing that certain attributes, such as attractive, positively correlate with makeup, but negatively with male and gray hair. Such insights suggest how society's perceptions align with these attributes, revealing underlying biases in attractiveness based on gender and aging. Following this, visualization of latent vectors discusses an intriguing method of visualizing facial images based on their latent representations. By extracting latent vectors from 1,600 randomly chosen images and reducing their dimensionality via the TSNE algorithm, the authors can cluster faces that share similarities in their encoding. The resulting visualization illustrates that images with similar backgrounds and those with smiling females tend to group closely, indicating the model's ability to capture relational aspects even without explicit annotations for certain features. Finally, in facial attribute prediction, the text concludes this section by addressing how the authors evaluate their model's performance. They utilize latent vectors for predicting facial attributes, a significant task due to the inherent complexities of facial variations. The study applies a sizable dataset comprising 20,000 images from Celebé to ensure robust testing and validation of the established methodologies, promising a comprehensive examination of their predictive capabilities. This methodical exploration reflects a sophisticated interplay between computational techniques and human interpretive frameworks, illuminating how technology evaluates and understands complex human features. In this section of the method, the authors detail the intricate processes employed for image processing and feature extraction in their experiments. Image cropping and feature extraction. The authors commence by utilizing ground truth landmark points to precisely crop facial portions from the original images, a technique akin to the Panda-L framework. These cropped images are then fed into an encoder network, which extracts what are termed latent vectors. These vectors represent compressed information about the facial images, which is crucial for subsequent classification tasks. The latent vectors serve as input to train linear SVM classifiers for predicting various facial attributes, with a total of 40 binary classifiers developed for each attribute present in the Celebi dataset. As a benchmark, the authors also train a different set of linear SVMs using 4096 dimensional deep features extracted from the final fully connected layer of a pre-trained model called VGGNet. This comparison is vital to establish the effectiveness of their proposed method against existing methodologies. An evaluation of the prediction accuracies places the author's method favorably against notable competitors. Their method achieves an accuracy of 86.95% using latent vectors from a variational autoencoder, VE, showing a competitive edge over methods like LNets plus ANET. Attribute prediction performance. The authors highlight specific attributes where their model excels, such as predicting wearing necklace, receding hairline, and pale skin. However, certain attributes like big lips and oval face pose challenges, likely due to their subtle nature compared to more visually distinct attributes like wearing hat and eyeglasses. Reconstruction loss in VAE models. Moving into the mechanics of variational autoencoders, the authors explain the critical role of a reconstruction loss, which evaluates how closely the generated image matches the input image. Traditional methods have shown limitations, leading to blurry outputs. To address this, the authors propose using feature perceptual loss, influenced by advancements in style transfer and image synthesis. By leveraging pre-trained deep convolutional networks, CNNs, they can gauge the perceptual similarity more effectively, enhancing the quality of generated images. While the feature perceptual loss exhibits significant improvements, it is acknowledged that challenges remain, particularly in achieving clear hair texture in generated images. Future endeavors could explore combining feature perceptual loss with techniques such as generative adversarial networks, GEN, for even better results. Insights from the latent space of VAE. The authors also emphasize the advantages of the linear structure within the learned latent space of the VE, where images can be transformed through linear combinations of their latent vectors. This structure opens avenues for attribute manipulation, allowing specific traits of an image to be altered while preserving others, a capability that aligns well with human cognitive understanding of facial attributes. Ultimately, this section lays a comprehensive foundation for the forthcoming experiments by illustrating not only the methods and techniques employed but also the underlying logic and expected outcomes, thus priming the reader for the detailed results and implications that will follow. Experiments. In this study, experiments focus on face image datasets to evaluate the proposed model, specifically comparing its performance against other generative models. An important aspect involves assessing how high-level feature perceptual loss aids in generating realistic facial images, as well as exploring the latent space for predicting facial attributes. Training details. The model is trained on the Celebi dataset, which comprises over 202,000 face images annotated with various attributes. The training process involves pre-processing images to a uniform size of 64 by 64 pixels, followed by using the atom optimization technique with a specific learning rate schedule. The model architecture includes a 19-layer VGGNet to compute perceptual losses, experimenting with various combinations to optimize performance. Qualitative results for image generation. Two alternative generative models were employed for comparison: the plain variational autoencoder, PVAE, and the deep convolutional generative adversarial networks, DCGN. The evaluation is split into two parts: random face image generation and face reconstruction. Results showcased in figures illustrate that PVE generates blurry images lacking in detail, while DCGN creates sharper images but suffers from implausible facial distortions. In contrast, the proposed method achieves a diverse range of facial features with better clarity, overcoming some limitations encountered with hair textures. Investigating learned latent space. A deeper analysis of the latent space begins by examining linear interpolations between different latent vectors. This method illustrates smooth transitions between various attributes, such as emotions and accessories. For instance, one interpolation demonstrates a gradual change from a non-smiling to a smiling woman. Furthermore, vector arithmetic on specific attributes, like adding a smiling vector, reveals patterns in how facial features can be manipulated, affirming the structured nature of the learned latent space. Overall, the comparison tables highlight the performance differentials among models, clearly demonstrating that the proposed model excels in generating high-fidelity face images while providing flexible control over visual attributes. The extensive analysis of reconstruction results and latent space manipulation sets the stage for a comprehensive understanding in the subsequent conclusion section. In this concluding section, the research highlights significant advancements in image generation through the innovative application of perceptual loss from pre-trained deep CNNs in variational autoencoders, VEs. The findings demonstrate that this approach yields superior performance, particularly in the generation of face images, outperforming traditional VAEs and generative adversarial networks, GANs. Furthermore, the study delves into the latent representation learned by the model, revealing its exceptional ability to encapsulate both conceptual and semantic details inherent to natural images. Notably, the model also sets a new benchmark for facial attribute prediction based on this robust latent representation. Overall, the research provides compelling evidence of the model's efficacy and contributes valuable insights to the field of image generation and representation learning.